Hello guys, we are back again, and today we are going to talk about enzymes. Well, first and foremost, what is an enzyme? An enzyme is a biocatalyst. Bio means it has to do something with living, and catalyst is anything that changes the speed of reaction. So this will change the speed. Either it will make it go faster, or it'll make it go slow of a reaction. Rx is reaction. What's a substrate? Substrate, so here's a reaction. A plus B is giving you C. A plus B are the substrate, the reactants. C is the product, what is being produced in a reaction. So first, let's see how enzymes can do this. Well, first and foremost, enzymes are just proteins. And if you have read the previous chapters, these proteins are folded. All proteins are folded, if you remember what we talked about, right? And when they're folded, they have a certain shape. So based on the shape, they have this nice wedge, or this groove, or this space into which a substrate can bind. So all enzymes have this area where the substrate is going to bind, and this is called the active site. When it binds, you get an enzyme substrate complex. This binding is absolutely necessary for an enzyme to change the speed of reaction. All right, we need to understand this. All right. Now, if you see this graph, there's nothing to get worried about. Here, if you see this graph, you notice that you require this much amount of energy for an activation energy without an enzyme. So if you have this reaction, A plus B is giving you C. So here what I'm trying to explain is you may have to heat it 500 degrees Celsius minimum of 2 hours, okay? But if you use an enzyme, same reaction, A plus B is giving you C, but now you're using an enzyme into this, you may just have to heat it for just 100 degrees Celsius, just for maybe 1 hour. So notice that the advantage of using an enzyme is not only are you changing the speed, in this case is going faster, but you're using less energy. This energy that is required for a reaction to occur is called activation energy. So this activation energy with an enzyme is so less. So here you're using less energy. Same thing I'm talking about in simpleton language. This would be can be shown. So here the bottom line is that if you use an enzyme, you use less energy, which is called the activation energy, for the reaction to take place. Another aspect, enzymes just don't speed up any reaction. They are very, very substrate specific. That means an enzyme will act on a certain substrate only. Let's say for example amylase. Amylase only works on starch in your mouth and converts it, this is a polysaccharide, and converts into a disaccharide, that's maltose. You don't have to memorize this, just understand that this enzyme is specific to starch. It is not going to work on a protein or a lipid. So why is that? Well, the reason is because we just said that enzyme is a protein, a folded protein. It has an active site. Into this groove, a substrate of a particular shape can fit. So the model to explain best is called induced fit model, which says not only the shape of the substrate is important, but also the type of substrate is important, because once the substrate binds into the active site, the enzyme folds around it, encloses it, and changes its shape, so that now what happens is it fits perfectly. All right, this is the induced fit model. All right, so here are the 6 attributes to an enzyme. Enzymes are proteins that are folded. They have an active site. They decrease the energy of activation. We understand these 3 points. Now, there's a new aspect. all enzymes have an optimum pH and temperature. Optimum means best. So this is the best pH and temperature that where they work the best. Remember, all enzymes are different. Different enzymes require different pH. Different enzymes require different temperature. There is no one hard and fast rule that works for all enzymes across the board. For example, the enzyme in your mouth works at a higher pH. The enzymes in your stomach works at a low pH. The pH in your stomach is very low. The enzymes in your blood has a higher pH. So same you and just different enzymes, the mouth enzyme and the stomach enzyme are going to be working best at different pHs. That is what I mean by optimum. So optimum pH, optimum temperature, they have this window, this narrow range where they are going to work best. But all enzymes, interestingly, denature at some temperature, extreme temperature and pH. And this can be seen, this can be understood because enzymes are folded structures. If you are going to mistreat it or expose it to extreme temperature, it is going to unfold, and once it unfolds, it loses its shape and therefore it loses its active site. That is something that you need to understand. Folded shape, it has a shape and therefore it has an active site. When it unfolds, it loses its shape and loses its active site. Therefore, no substrate now can bind, and therefore what happens is if substrate cannot bind, you cannot get the complex and enzymes will not work. So denature means it will lose its function. Okay? It cannot work now. All enzymes are substrate specific. We talked about that. They will not work on any substrate, any reactant. They are very, very specific. The enzymes that break down lipids cannot break down protein. The enzymes that can break down starch cannot break down protein. All right? So here, what are the factors that affect enzymatic speed? Well, first of all, substrate concentration. You need to have an enzyme concentration. So you need to have a perfect ratio of substrate and enzyme. Like when you're making a cake, you have to have a perfect ratio of the flour that you use as well as the baking powder. You just cannot use any ratio. Saying substrate and enzyme ratio needs to be optimum, and again this ratio varies from enzyme to enzyme. Third, optimum temperature and pH where they work best. Like I said, there are some forms like we talked about earlier, the archaeal forms. These are forms that live in extreme environments. Let's say, for example, archaea that live in very, very cold environment, they will have, the enzymes will have a different optimum pH. You do not live, you are not an archaeal first. You don't live in extreme environments, so of course what happens is you have an optimum, your enzymes have a different optimum temperature and a pH. Okay, cofactors and coenzymes. Cofactors and coenzymes are helpers. So they don't interfere, but they help an enzyme work better. Cofactor is like a big umbrella, all right? It's a big umbrella. And cofactors are many types. So cofactors can be coenzymes. And what are coenzymes? Coenzymes are non-protein, they're non-protein organic molecules. So the cofactors can be one. It can be a coenzyme. It can be a metal ion, like say for example calcium, magnesium, potassium, etc. Or it can be a prosthetic ion or a prosthetic cofactor. So let's focus on coenzyme. Coenzyme are non-protein organic molecules, and these come, like for example NAD, these are coenzymes. So NAD, what happens is, as a coenzyme, it will bind to an enzyme and will move away. It is not going to be permanently bound. It helps an enzyme work better. Example of coenzymes are vitamins. That's why it's important that you eat vitamins. Why? Because a coenzyme vitamin is a coenzyme, it helps an enzyme work better. All right. A metal ion, you understand metal ions, like for example potassium. Here I'm going to write this out here, like for example potassium, for example sodium. These are again specific for a reaction. Calcium, these are metal ions. Cofactor could also be prosthetic cofactor, which remain bound to an enzyme. They don't leave the enzyme. Like a coenzyme can leave. Once its work is done, it leaves. A prosthetic is part of an enzyme. It doesn't leave. Example is the heme part of the hemoglobin. Okay. Inhibitors. Inhibitors, I'll talk about inhibitors in just a minute. So this is just explaining to you about cofactors and coenzymes. Keep in mind, cofactor is a big number. It's like a big umbrella, and different. Okay, I can explain this better. All coenzymes are cofactors, but all cofactors are not coenzymes. All right, like biology 103 students are Calhoun students, right? But all Calhoun students are not biology 103 students. Same thing. Cofactor is a big umbrella. Coenzyme is a type of cofactor. Clear? All right. So we were talking about inhibition, and there are inhibitors. So inhibitors are those that will not allow an enzyme to work efficiently. And there are many types of inhibitors. There are many types of inhibition: competitive, non-competitive, feedback. All right. So competitive is the one which binds to an enzyme. So here what happens is the inhibitor looks like the real substrate. So what it does is it will bind to the enzyme. Here's my enzyme. So the inhibitor is binding to the enzyme instead of the substrate. And therefore what happens is it will not allow the enzyme to work efficiently. Okay. The non-competitive, what it does is, here it is not going to bind to the active site, but it will bind close to the active site. Therefore it is going to block the actual substrate from binding into the active site of the enzyme. Once again, competitive, remember, the inhibitor looks like the substrate, binds to the active site. The non-competitive, the inhibitor binds close to the active site, and it therefore blocks the entry, binding of the substrate to the active site of the enzyme. Feedback inhibition is easy. Here what happens is their products, they accumulate, and because of accumulation, so the products are accumulating, the products are here, and they are accumulating, and they are blocking the actual substrate from coming and binding to the active site of the enzyme. So this is the enzyme, here are the products that are accumulating, here's the substrate, it wants to come and bind, it cannot bind. This is just a picture. It's trying to explain to you competitive and non-competitive. Competitive, watch that here's the inhibitor, it is binding, the green, it is not allowing the actual substrate to bind. It can be easily overcome. You just increase more substrate, and therefore what happens is the inhibitor is outnumbered, cannot bind, and that's fine. Here what happens is more of a problem. Non-competitive, it doesn't bind to the active site, but binding close, changing the shape, and because it changes the shape, what happens is it blocks, or what happens is changes the shape of the active site, so distorted active site cannot bind to the substrate. So hopefully this is clear to you. I think this is the last slide. Yep. And we cannot bind, anymore, excuse me. So here, hopefully it's clear, and if you have any questions or concerns, please call me, please talk to me. So thank you, and have a great day. Bye.